Short period, but I think we can get through this. This is the kind of stuff we were talking about. This is where we sort of left off last week, right? We were talking about solving quadratic equations, and that's what this whole unit is about. We're only on the easy ones right now. Later on in the unit, you're going to see all of them at the same time, and it's going to kind of be up to you to choose the appropriate strategy based on what the quadratic equation looks like. So even though we're practicing doing the same thing over and over in this first section, kind of try to think about why you're doing it, because later on there will be different approaches we could take. We won't be able to do this all the time. What's our strategy here to solve for x? What would the steps be to solve for x? Say it again. PEMDAS backwards. Okay. The distribute, we'll talk about that. There's actually a reason why we can't do that, and that'll come up. We'll talk about that. So we're going to do PEMDAS backwards because our goal here is to isolate x, right? How come? What is it when you look at this where you say, okay, this is one where I isolate x? There's only one x, right? That's our rule. If we have just a single x that we can point to, and there it is, if we're just trying to find just real solutions, then we can always just reverse order of operations and isolate the x to solve the equation, right? So what's that look like here then? So we're isolating it. Reverse the order of operations. What do we do first? Think about it. Let me rewrite this. What's first? Subtract 10. Good. Okay, that's good. So there's one step. Okay, now what? Okay, I've heard a couple things. I heard distribute the negative 2. Okay, I can't do that. How come? And this is really important. Yes, sir.
You can't distribute a negative number.
No, I can distribute a negative number. That's not the problem. What is it that I can't do? You can't? Exponent. There you go. So here's the red flag that we're seeing. I can't distribute the negative 2. If that weren't there, I could. It'd be fine. Then I could. But because this whole quantity is being squared, I can't distribute first and then square it. That doesn't make sense. Distributing is not an isolating step, is it? That's a simplifying step. Everybody agree? When we're isolating the variable, everything we do is just to try to remove stuff from the left side and move it to the right side in this case. Distributing doesn't really do that. Sometimes it's okay to do, but it's a simplifying step. Well, if I'm simplifying, that means I'm going down in this direction, right? Distributing the negative 2 would be the multiply divide step. But what has to come before that? Exponents, right? I would have to first square this whole thing out and then distribute, right? And we don't want to do that. That's the opposite of what we want to do. We just want to, if we square that whole thing out, it's going to be a mess, and it's going to be a harder equation to solve, right? So we don't want to distribute. If I've ever got an exponent there, can't do it. What am I going to do instead? Divide. I'm going to divide, right? I can't square root yet because I've still got some multiplication going on. When we're isolating, remember that we don't get to deal with the parentheses until the very last step, right? So we're only looking at stuff that's going on outside of the parentheses. So I'm just going to put my hand right there. We don't care what's inside. Well, outside of the parentheses, there's two things going on, right? The parentheses are being squared, and they're being multiplied by negative 2, right? Mm-hmm. Well, what do I do first? If I'm isolating, do I deal with multiplication, division, or exponents first? Multiply, divide, right? If I'm isolating, I'm going bottom to top. So I've got to undo that multiplication by dividing each side by negative 2, right? Okay, so that cancels the negative 2s. Good. Everything I've done has taken something away from the left side to help us isolate that x, right? Okay, what's that leave us with? Well, that leaves us with all this stuff is gone. Now I've just got the quantity negative 2x plus 3 squared equals negative over negative is positive 98? 98? Okay, now what? Now I square root, right? To get rid of that guy, right? Okay, so that's going to give me what? If I square root everything, it's going to cancel the squared. And now I don't even really need the parentheses anymore, do I? We got to that layer, but I don't really need them anymore. They're not doing anything. So if I square root both sides of an equation, what do I always have to include? Plus or minus, right? That's got to be there. Ooh, and here's the problem, though. Square root of 98. Square root of 98 that doesn't work out so nicely like all the ones did last week, right? 98 is not a perfect square. If I put it in a calculator, I would get a decimal. But a decimal is not what I'm going to be asking for. I'm going to be asking for exact solutions, right? And so we gotta take a pause on this problem and think about how we're going to simplify that. How are we going to simplify something like the square root of 98? Okay, there's a trick that I'm going to show you guys. I don't think we haven't talked at all about this, right? That's right. Okay, we shouldn't have. Good. Okay, in order to do that, there's a couple little skills we need to practice first. So one of them is we got to be able to write a number in terms of its prime factors using a factoring tree. Okay, you've done this before, I'm sure, but it may have been a while. So let's go through this process. If I want to write 135 in its factored form, written in terms of just a product of prime factors, I start with the 135 at the top of the tree, and I'm just going to break it into factors. And each time I break it into a factor, I'll see if I can go further with that. Okay? And I only stop when the number at the end of a branch is a prime number. What's a prime number? 7's an example. What's another prime number?
30.
13. What's another one? 3. What's a non-prime number? 2. No, 2's prime.
Oh.
But 10's not. How come? Okay, if something divides into it other than 1 and itself, right? So a number that's only divisible by 1 and itself is a prime number, right? So those are the only kinds of numbers we want to have left when we're all done with this. Well, what are two numbers that multiply to 135? And there's nothing special about the ones that you pick. Just any two that multiply to 135 will work.
1 and 135.
Okay, but we don't want 1. That's okay. I should have been a little more specific. We don't want 1s. Now, one of them's there's a pretty obvious one that we know is going to divide into 135. What's that? 5, because it ends in a 5, right? So we know 5 goes into it. How many times? 5 goes into 13 twice with how much left over? 3, I guess, right? And 5 goes into 35 7 times. Okay? So 5 is prime, so that branch is done, but 27 is not, so we can split that up again. 3 and 9. 3 is done, but 9 is not. We can split that up. 9 breaks up into 3 and 3. Okay, so then these are all prime numbers down here, so everything at the end needs to be prime, right? They all are, so we're done. So what is 135 written as a product of prime numbers? 135 equals, let's do the 3's first. I've got 3 times 3 times 3 times 5, right? But that's an inconvenient way to write that. What's a simpler way to write that? 3 times 3 times 3 is 3 cubed, 3 to the third, right? So the simplified version of this answer would be 3 cubed times 5. Okay? Try that one real quick in your notes. Grab your notebook, set your notebook. And try it. Yeah, just got to pass it. Okay. Help us out here, somebody. What are two numbers that multiply to 1,008? Emily, what do you get?
2 times 504.
Good. Now you know it's even, so guarantee 2 goes into it. How about 504? About 504. What's a number that divides into 504? Say it again. Oh, there you go. Okay, so you know that 2 does because it's even. And then 252. Okay. What else? So that's even, so another 2. And then 126. That's even. So another 2. And what, 64? 63, whoops, you're right. And what about 63? Say it again, 3 and 21, okay. You could, I would have done 9 and 7, but 3 and 21 works, that's fine. And then 21.
That's a 3.
Okay, and then we're done, right? All the branches end in prime numbers. So what are we gonna write this one as?
2 to the 4 and 2 to the
Okay, good, so we got, how many 2s? 1, 2, 3, 4 2s. So 2 to the 4th, 2 3s, so 3 squared, and a 7. Okay, it's prime factor form. Okay, so why are we doing this? Well, here's why we're doing this. Because if we want to simplify a radical, the easiest way to do this is by looking at its prime factor form. Okay, so let's take, if we want to simplify the square root of 360, let's take the radicand, which is just a fancy word for the number inside the radical. Okay, let's take the number inside and let's break it up into its prime factors. So 360. Now, if the number ends in 0, 10, good, we know that 10 goes into it. So this is 10 times what?
37.
Good, and 10 breaks up into 5 and 2, good, okay. How about 36? 4 and 9. Yeah, how about 4? How about 9? Okay, why do we do that? Okay, well, here's why we do that. If I break up the 360 into all these products, let's take the 2's for example. How many 2's do we have there? It looks like we've got 2 times 2 times 2, so I've got 2 cubed. Okay. What is the square root of 2 squared? 2. If I square root a square, doesn't it undo the square? Right? What's the square root of 17 squared? Aha. And if I square something, it just means I'm multiplying it by itself, right? So what if we took those factors and we broke them up into couples and singles? Okay? So we've got, where do we see some couples? Well, I see, and I always put the couples in boxes and the singles in circles, but you can do it differently if you want to. So here's a couple of 2's. Here's a couple of 3's. What else do we have? Well, we have a 5 and a 2. That 2 might seem like it's a couple, but it's not. That's kind of the oddball, right? That one was left out. These 2 were in a couple. The 5 and the 2 end up being singles. And so we could write the square root of 360 as the square root of, isn't that just 2 squared, right? So the square root of 2 squared times, isn't that just 3 squared? Times 5 times 2. So there's a property of square roots that tells us if I have a square root of a product, I can break that up into separate square roots if I want to. when you write that product down, or write that property down, it just looks like this. The square root of A times B equals the square root of A times the square root of B, where A and B are just numbers. Yes, ma'am?
Why is it more beneficial to write it out this way instead of just doing 2 cubed?
You'll see. You'll see why in a second. So when I write this out separately then, this just becomes the square root of 2 squared. That just becomes the square root of 3 squared. And let's go ahead and group all the singles together. We could make them separate, but we don't really need to. Well, what's the square root of 2 squared? 2, aha. So that 2 ends up outside of the radical. The square root of 3 squared is 3, and 5 times 2 is a 10, right? And so our final simplified answer is just going to be 6 times the square root of 10. When we're simplifying a radical, our only goal is to get as much of the number outside of the radical as possible. That's how we simplify it, right? So we can make this process a little simpler. We didn't even have to go through this whole thing. We could have jumped right directly to our answer if you remember one little saying. It's easy to remember. This is the key. Couples go out, singles stay in. That's it. If you remember that couples go out of the radical, singles stay in the radical, then that's the key, right? Right from this part right here, we had it made. All we had to do, what was this, 1,008? Is that what original, no, 360. All we have to do is whatever we have a couple of, we have a couple of 2s, and so that means that I'm going to put 1 2 outside. I have a couple of 3s, so 1 3 goes outside, and all the singles just stay inside. So that takes us right to our answer, doesn't it? We just end up with 6 times the square root of 10. Okay? Now let's try one of those. It's really simple. Let's try this guy. Square root of 110. Let's factor 110. Okay, what's 110 work out to be? 11 and 10. What's 10 break up into? Are there any couples at all? No, they're all singles. So the square root of 110 is just the square root of 110. Nothing came out. Okay, that is a simplified form. Okay, try another one. Oops. Try this one. Let's do square root of 54. Try that. We want to hazard a guess here? What did we get? What do you think? 9 times the square root of 6. Okay, it's very close. We want to change that slightly? No. We're close. Three times the square root of 6 is right. Okay, it was a pair of 3s that made the 9. That's all it was, right? You see what you did?
Yeah.
Okay, so let's go through how we got that. So the correct answer is 3 radical 6. How do we get there? Walker, what are some numbers that multiply to 54? 2 and 27. How about 27? What's another, what's, okay. And 9, 3 and 3. Okay, so do we see any couples? Okay, there's a couple of 3s, and there are some singles, right? So what's our answer going to look like then? Well, anything that I have a couple of, now I don't put both 3s out there, I just put what I have a couple of, right? I have a couple of 3s, so there's a couple that goes outside. Couple of 3s, that's the only couple, so all the singles stay inside, right? So our final answer then just looks like 3 times the square root of 6. Okay? Try another one. Let's do what do we get? What do we get? 5 times the square root of 3. Okay, good, good. Jocelyn, what are factors of 75?
5.
And what is that? 15? Okay, good. How about 15?
35.
Okay, so those are all prime factors, right? The ends of the branches are all prime numbers. What do I have a couple of? There's a couple of 5s right there, right? So I know I'm going to get a 5 outside, and I've got only one single that's a 3. And so there's my 3 inside. Okay, one more. We'll call her good. So let's do this one together. So what are factors of 108? 12 and 9. Okay, good. How about 9? 12. 4. Okay, so there's a couple. There's a couple. There's a single. So what numbers go outside? 3 times 2 times square root of 3. So we get 6 square roots of 3, right? Okay, what if you had done this, same problem, what if you had factored this a little differently? I just want to make one quick point. What if you had said, okay, instead I could maybe say that's something like 3 times 36. What'd you do? You already could do 4 and 27. If I do 3 and 36, there's a way that you, in a way that's actually a little bit maybe easier way to do it. How come? Anybody see a shortcut here? Max and C7, what do you see? 6 and 6, right? So 36 breaks up into, it's a perfect square. It splits into 6 and 6. Now, do I need to break that 6 down to a 2 and a 3 and that 6 down to a 2 and a 3? I I really don't need to, because I've already got a couple there, right? I can stop. I could just say, here's a couple of 6s and a single 3, and just get my answer is 6 times the square root of 3 in one step. You have to do it that way? No, it's no big deal. But if you can pick out a factor that's a perfect square like 36, it makes it a little bit easier, right? Anybody see the trick?
Yeah.
Are we out of here like now?
Yeah.
Oh, 1 minute? Let's call it quits then. Okay, so would I do this then? There's some assignments up there. Right away, jump in and do the prime factorization. I think it's only 4 problems. Probably do it in 3 minutes. It's super easy. And then after that, do the simplifying square roots. And then we'll pick this up later in the week and go from there. Yes.
So next week, I'm gonna be gone all the whole week.